Okay, now we're going to talk about the second derivative, and it tells us the concavity of the graph. So first, let's define what concavity is. This is the technical definition of it. A graph's concave up at a point if the tangent at that point is below the graph, and it's concave down if the tangent at that point is above the graph. So if you look at these, we could apply that definition, but really this is the way that I remember concave up versus concave down. Concave up is shaped like a cup. Concave down is shaped like a frown. So with these graphs up here, this one is increasing, and notice this part of the graph. It's like half of the smile or the cup. So this is concave up. And notice if you drew a tangent line somewhere on here, it would go below it. This is decreasing, but it's also concave. Looks like half of this. It's concave up. Now the other two, this one is increasing, and it looks like half of a frown. Looks like this half of a frown. So frown down, concave down. And this one looks like the other half of the frown, so it's concave down. And it's decreasing. Now there's a calculator on Desmos you can look at, and this is a clickable link on the PDF file. But I want to play with it for a second. Let's see. Here's a cubic graph, and over here on this portion, from about here back, it's concave down. It's shaped like a frown. And if we move I've got a tangent line here that we can look at. The tangent line is above it. But once we get over here past this point here, the tangent line drops below. So it's concave down over here, and then it's concave up over there. Now, the way you find concave up and concave down, it's almost exactly like the way you find increasing and decreasing, except you use the derivative, the second derivative instead of the first. So let's look at a couple of things here. It says consider the graphs of y equals x squared and y equals minus x squared. Y equals x squared, we know, looks like this. It's concave up everywhere because it's shaped like a cup. And y equals minus x squared looks like this. It's concave down everywhere. Well, if you look at the derivatives of these, I'm going to move this over here. If you look at the derivatives, y prime for this graph is 2x, and y double prime is is just 2. Getting ahead of myself. So the second derivative is positive. Over here, y prime is negative 2x, y double prime is negative 2. The derivative is negative. So the way to think of this is up, cup, and positive, second derivative, and then down, frown, and negative. So it kind of goes together. Frown is negative, and up is positive, so it works out. Here's the here's that stuff basically written as a fact. If f double prime of c is positive, the graph is concave up at c. If f double prime is negative, then it's concave down at c. So to find the intervals of f of x where it's concave up and where it's concave down, a lot of the time the book will just call these the intervals of concavity. What you do is exactly the same as before, except you use the second derivative. So you find the hypercritical numbers of f of x. Now, hypercritical number is not a standard term. You won't find it in the textbook. If you Google it, it may or may not turn up, but it's not a standard term. But it's the word I use that means the numbers that make the second derivative 0 or undefined. So what you do is you find the hypercritical numbers, you cut up the real number line into those, And then you pick test values, and that tells you where it's concave up and down. And this definition, a point on the graph where the concavity changes, is called an inflection point. So let's do this example here. Find the intervals where this cubic function is concave up or concave down, and find any inflection points. Okay, so we've got to find the second derivative. Let's see, f of x is going to be 4x squared plus 2x minus 5. Then f double prime of x is going to be 8x plus 2. So I'll take that and set it equal to 0. And that's nice. It just gives me 8x is -2, so x is -1/4. That's my hypercritical number. So I'll come over here and I'll cut the real number line up at -1/4. And I'll pick test values for both sides. Over here I'm going to pick 0, over here I'm going to pick -1. And I'm going to put in f double prime. So f double prime of -1 is going to be 8 times -1 plus 2, which is negative. F double prime of 0 is just 2, which is positive. So that tells me that my original graph, f, let's see, negative, that's concave down, which is a frown, positive concave up, which is a smile. You can also think of this, I guess, as frowns and smiles for plus and minus. So this tells me that the graph is concave up on -1/4 to infinity, and concave down on -infinity to -1/4. And since the concavity does change there in the middle, we have an inflection point at x equals -1/4. Or you could put -1/4 and then plug -1/4 back into the original function to get its y value. Now I'm just going to do that on my calculator. -1/4 well, let's see, 4/3 times -0.25 cubed plus -0.25 squared minus 5 times -1/4. So that's going to be plus 5/4. If I did all that right, I get 31/24. And let's check this on Desmos. Now, I've got my fancy Desmos sheet here. I'm going to change this to just a regular Desmos sheet. F of x equals 4/3 x cubed plus x squared minus 5x. All right, so we've got this. Let's see, let me pull this up further so we can see more. So this is our function, and if I highlight the function, notice it highlights the max, the min, and the intercepts. But let's do f double prime. It gives me this line here. And notice it crosses the axis here at -0.25. And I should be able to check my my inflection point by putting in -0.25, comma, f, -0.25. So there it marks the inflection point. And I guess if I wanted to make Desmos compute the value for me, I could just put in f of -0.25 And it gives me that number, which I'm going to compare that to 31 over 24 on my calculator. 1.291, and then repeating sixes. So yeah, that's it. And that's the inflection point there. All right, I want to do a few more examples, but I'm going to stop this video here.